When you look at a truly massive plane, like a C5 Galaxy, your eyes probably go straight to the wings, maybe the giant engines. But today, we're going to talk about the unsung hero of these incredible machines, the part that performs a feat that's borderline impossible on every single flight, the landing gear. It's an overlooked masterpiece of engineering, and you're about to find out why. Yeah, we all have this image in our heads, right? A graceful, almost delicate kiss with the runway. But for the heavy lifters of military aviation, the reality is, well, it's way more brutal. And for the engineers who design this stuff, that gentle image is a fantasy they have to completely ignore. Let's just call it what it is. Every single time one of these half-a-million-pound monsters comes back to Earth, it is, for all intents and purposes, crashing. It's just a very, very precisely managed high-energy impact. The goal isn't to be gentle, the goal is just to be survivable. And that really is the million-dollar question, isn't it? How can a machine that weighs hundreds of tons literally slam into the ground, sometimes in the worst possible conditions, and then just roll away like it's no big deal? The answer is hiding in a brilliant system of shock absorption and force distribution. Okay, so first things first. We have to wrap our heads around the sheer scale of the forces we're dealing with here. This is not your car hitting a pothole. This is a calculated, high-stakes collision. Let that number sink in for a second. 600 feet per minute. That's a drop of 10 feet every single second. To put that in perspective, imagine dropping a fully loaded semi-truck from the top of a 3-story building right onto its wheels. That's the kind of energy we're talking about, and the gear has to just soak it all up, every single time. And it's not just a simple up and down force. Oh no, the gear is fighting a war on multiple fronts at the same time. You've got the brutal vertical impact, of course, but you also have insane side loads from crosswinds trying to rip the wheels off sideways. You get twisting forces if one side touches down before the other. And then there are the massive weight shifts during an emergency brake. It is a 3-dimensional physics nightmare. So, how in the world did engineers build a solution for such a violent problem? Let's take a look under the hood, because this is where the real genius is hidden. This right here is the heart of the whole system, the oleo-pneumatic strut. Here's how it works. The wheel hits the ground. Bam! The strut immediately starts to compress, forcing hydraulic fluid through these tiny little holes. This basically turns that raw, violent impact into manageable heat. But the real magic happens at the top, where a chamber of compressed nitrogen gas acts like a perfect, powerful spring, absorbing that final, massive punch of energy. You know, this analogy is just perfect. It takes a concept we can all kind of understand, a really nice bike suspension, and then scales it up to a level that is just mind-boggling. It's the exact same principle, just engineered for forces that would literally vaporize any normal vehicle. Okay, 28 wheels. Why on earth would you need 28 wheels? It's not just about holding up all that weight. No, this is a core survival strategy, and it gets right to the heart of impact physics. It's all about spreading the load. Each one of those 28 wheels is a point of contact. So instead of one massive shock hitting just a few points, the C5 distributes that colossal impact across a huge area. This dramatically lowers the stress on any one component. And it also means that, hey, if a few tires blow out on landing, it's not a catastrophe. The plane can still land safely. And this stat right here, this brilliantly illustrates one of the biggest differences. Stroke travel is just a fancy way of saying how far the gear can compress. Your average commercial jet has about a foot, maybe a foot and a half of travel. A C-17 has over 3 feet. That extra distance is basically life insurance. It gives the gear way more time and space to slow the plane's fall, which massively reduces the peak forces on the airframe. Okay, so we get the basic hardware. It's tough. But how does it actually perform when things get truly chaotic? Like when the runway is barely there or the wind is trying to throw the plane into the next county? We've all seen those wild videos, right? The plane comes in looking like it's flying sideways, crabbed against the wind, and then, bam, it slams onto the runway and instantly snaps straight. How does the gear not just shear clean off? It survives because it's literally designed to twist and absorb that energy. It uses what are called articulated trunnions. Think of them as massive rotating joints that let the gear pivot. Giant braces called torque links keep the wheels from going all wobbly, and the whole structure is built to channel that insane sideways force away from the gear itself and into the strongest part of the plane, the wing roots. It's brilliant. Now, as intense as a crosswind is, the brownout is pretty much the final boss of landing challenges. This is when a plane lands in a dusty or sandy place, and it kicks up a cloud so thick the pilot can't see anything. The landing is basically blind, hard, and totally chaotic. The gear is hardened for this exact nightmare scenario. The anti-skid system is programmed to work on dirt and sand, not just perfect asphalt. All the seals are heavy-duty to keep out grit that would destroy normal hydraulics. The side bracing is reinforced for impacts you can't even see coming. And the tires themselves are overbuilt to flex and absorb impacts on rough, totally unprepared ground. So how does this all come together? Well, the incredible hardware is really only half the story. The other half is a whole philosophy of resilience that's baked into the entire system from day one. This is the guiding principle. It's not failure is unlikely, it's failure is not an option. So the entire system is designed with the absolute expectation that things will go wrong. The goal is just to make sure that no single failure can ever lead to a disaster. And here's what that actually looks like. There isn't just one hydraulic system, there are several. If they all fail, there are mechanical locks to hold the gear down. If the electronics go out, there's a manual crank to get it down. Each leg of the gear runs on its own circuit, so a problem on the left side can't take out the right side. It is defense, in depth. And this resilience doesn't stop. It extends through the gear's entire life. Specialized units don't just patch these parts up, they completely overhaul them. They use incredibly advanced tech to repair damage at a microscopic level. So a worn-out strut isn't just fixed, it's returned to factory new condition, ready to go out and face another lifetime of controlled crashes. And that really just reframes how you look at the whole aircraft, doesn't it? The wings are amazing, they keep it in the air, but the landing gear, the legs, that's what makes the mission repeatable. It's the shock armor, the survival system that allows these giants to come home safely from the toughest places on Earth. So the next time you see a plane landing, look past the wings and give a little nod to the legs. It really makes you wonder what other incredible superpowers are hiding in plain sight, quietly doing the impossible for us every single day.